All right, here is the packet problems that we did from lesson 5, 6, and 7. I'm just going to go over them real quick. So this first one is just asking if to go from P to Q, would the scale have to be greater than 1, less than 1, or equal to 1? So pretty much anytime you go from a smaller to a larger size, you have to increase that size, and in order to do that, your scale has to be larger than 1. Because anything times 1 is itself, so anything larger than 1 gets bigger, anything multiplied by something smaller than 1 gets smaller. Okay, so P to Q, as you can see, Q is bigger than P, therefore it had to be greater. Same with P to R is bigger, so it had to be greater. With Q to S, it went smaller, so the scale factor had to be less than 1. From Q to R got bigger, so that had to be greater. From S to P, they stayed the same, so that's a scale factor of 1. Anything times 1 is itself. R to P got smaller, so it'd be less. And then P to S, it would be equal once again. Okay. So number 2, triangle S and triangle L are scaled copies of one another. What is the scale factor from S to L? So all we have to do is see how many units this is down here, which is 2, and then look at the bottom length on the next one, because remember, a scale factor, whatever you multiply the original by, gives you the new dimension when you multiply by the scale factor. So 2 times 2 would give you 4. So the scale factor would have to be 4. No, sorry, would not be 4, would be 2, because you're doubling it. Now to go in reverse, so from 4 to 2, well, that's just half of the original measurement. So now this scale would be 1/2. And what you should notice here is that to go from the small to the large, it was 2. To go from the large to the small, it's just that divided by, or the reciprocal of what you multiply. Because when you multiply by 2, you're really multiplying by 2 over 1. The reciprocal of a fraction is just that fraction flipped. Okay, hence where we get this 1/2. It comes from 2 over 1, which is just 2. All right, so likewise on this next one, it says triangle M is also a scaled copy of S. The scale factor from S to M is 3/2. What is the scale factor from M to S? So now we know from small to large, it's 3/2. So we're going to follow what we did up here, where you take the reciprocal when you work backwards. So the reciprocal of 3/2 is 2/3. And if you think about it, if it's a triangle that is 1.5 times bigger, so 1.5 times of 2 is 3. So now you go from 3 to 2. Well, if you divide 3 into individual sections, the other one is 2 of those thirds that you divided it into. All right. Number 3, it says the two squares with the same side length are scaled copies of, sorry, let me read that over again. Okay, are 2 squares with the same side length scaled copies of one another? Explain your reasoning. So 2 squares that have the same side length, they have the same angles, and all the sides are adjusted by the same scale factor. That scale factor would just be 1. So yes, yes, they would be scale factors. Okay, number 4, quadrilateral A has side length 2, 3, 5, and 6. Quadrilateral B has side length 4, 5, 8, and 10. Could one of the quadrilaterals be a scaled copy of the other? Explain. If it's a scaled copy of the other, then you will find one factor that you can multiply all of these original dimensions by to get your corresponding dimensions of the other one. So to start off, I said, well, 2 times what gives us 4? Well, 2 times 2 equals 4. Therefore, if a scale factor of 2 works for all of the dimensions, then they would be a scale copy. So I took 3 times 2 and I got 6. 6 is not 5, therefore you would say this is not a scale copy. Okay, number 5, all ratios that are equivalent to 12/3 or 12:3. So once again, you're just going to look at, is there a number we can divide both numbers by to get the new ratio, or multiply by? So this first one here, well, I know 12 divided by 2 gives me 6, but when I divide 3 by 2, I do not get 1. Therefore, 6 to 1 is not a ratio. The second one, I just know that my first number is bigger and my second one's larger, so this can't be a equivalent ratio. Right? 4 to 1, 12 divided by 3 gives me 4. 3 divided by 3 gives me 1. So this checks off. This is a scale factor of 1/3, so that works. Next one, 24/6. So same thing, 2 times 12 gives me 24. 3 times 2 gives me 6. That matches up, so that one is equivalent. The next one, I know 24 and 6 is equivalent, so 15 and 6 cannot be equivalent. Likewise with F, if you multiply both the original by 100, so 12 times 100 gives me 1200, 3 times 100 gives me 300. Once again, the same scale factor, multiplied both of them to get my new numbers, so that does work. And then the last one, 112 and 13. 12 times, you're almost close to 10, would give you 120. 112 is fairly close to that, so it'd be 9 point something. But 3 times 9 would be 27, so I can see that that one's not going to be an equivalent ratio. Okay, so moving on to lesson 6, practice problems. It said on the grid, draw a scale copy of the polygon Q using a scale factor of 2. So if it's a scale factor of 2, you're going to double every side, or you're going to multiply the original side by 2. And so that's what you'll see I did here. I went from 2 on the side to 4, 3 to 6, 1 to 2, 4 to 8, 2 to 4, 6 to 12, and then these I doubled as well from 1 to 2, 1 to 2. Okay, so that does the first one. There's the drawing. Everything is 2 dimensions big, or 2 times the original dimension. Then it says compare the parameters of the area of the new polygons to those of Q. So the parameter is the sum of all sides. So when you add up all the sides, you get 20 on the original. When you add up the sum of all sides on your scale drawing, you get 40, which checks out because if you double the parameter, then you're also going to have to, if you're doubling the scale, you're going to double the parameter, which gives you 40, and that checks out here. You just doubled the parameter as well. That's the dimension that has to also follow that scale of 2, which it does here. All right, here it tells us that there's a right triangle has an area of 36 square units. So this would be similar to what we did in the notes. And the big takeaway there in the notes was that the area changes by the scale factor squared. So whatever the original area is, you're going to multiply that by the scale factor squared. And scale factor squared just means the number or the scale factor multiplied by itself. So that's what I did here. So 2 squared times 36. 2 squared is 4. 4 times 36 gives me 144. Likewise, with a scale factor of 3, we're going to square that 3 and then multiply that by our original area. 3 squared is 9. 9 times 36 gives us 324. Okay, next one, 5. So same thing, 5 squared times 36. 5 squared is 25. 25 times 36 gives us 900. Okay, same thing with the fractions. We're going to multiply those or square those scale factor with a fraction, then multiply that by 36. when you square 1/2, you get 1/4, because 1/2 of a half is 1/4. 1/4 times 36 is 9. And really that just becomes 36 divided by 4. Okay, and the last one, 2/3. So same thing, we're going to square 2/3. You're pretty much just multiplying both numbers by themselves. So the numerator becomes 4, because 2 times 2 is 4. 3 times 3 is 9. Now we multiply that by 36, and you get 16. And once again, when you're multiplying a whole number by a fraction, you can either multiply it by the numerator first, then divide by the denominator, or you could divide by the denominator and then multiply by the numerator. And for me, that's just easier, because I know 9 goes into 36 4 times, and now I can just take 4 times 4 and get 16. All right, number 3, it says Diego drew a scale version of a polygon P and labeled it Q. In the area, the polygon P is 72 square units. What is the scale factor? Did Diego use? What was the scale factor? What scale factor did Diego use to go from P to Q? Explain your reasoning. All right. So to find what we multiplied 72 by to get to 4.5, we have to undo that multiplication. So we divide those two numbers. 72 divided by 4.5. When you do that, you'll get 16. Okay, so we're going to take that number and put it under 1. So 1/16, because once again, we are going from a larger number to a smaller number, so our scale factor has to be less than 1. And so we got 16 here, but we know that since it's a reduction, it's 1/16 that we're multiplying by. Okay, so that gives us the number that we're multiplying by. 72 times 1/16 equals 4.5. But now, remember that the area of a figure changes by the scale squared. So pretty much this 1/16 is the scale squared. We need to find out what the square root of that is to find the actual scale. So the square root of 1/16 is actually 1/4. Therefore, our scale factor is this 1/4. Okay, number 4 here, all it's asking us to do is from this original polygon, what is the scale factor to get to A, to get to B, to get to C, and to get to D? Well, just looking at it, I went from 2 to 1. Well, 2 to 1, that would be half of the original length, so my scale factor is 1/2. On B, you notice you go from 2 on the original to 4. Well, to go from 2 to 4, you multiply by 2, therefore my scale is 2. On C, you go from 2 to 3. Well, to go from 2 to 3, you have to multiply by 1.5 or 3/2 to get 3 from 2. And so the scale factor is 3 to 2. And on D, you notice you went from 2 to 2, which stayed the same. So then the scale factor had to be 1, because anything times 1 is just itself. All right, number 5, we're just looking for what number do you have to multiply 1/7 by to get 1. That would be 7. If you have 7/7, you would have a whole. Likewise with B, same thing. If you had 11/11, you would have a whole amount. And then the last one, this is just thinking backwards. So now we have the 1, but now instead of multiplying by the fraction, we're dividing. So it's saying when you divide 1 by 1/5, or how many fifths make up a whole, it would be 5. All right, lesson number 7, practice problems. This first one, it gives you a scale down here. And then you have to use that scale to find the actual dimensions. So when I measured with a ruler, this 10 feet is equivalent to 2 centimeters. You might have something a little different, and that's okay. Your numbers should come out fairly close still. So 2 centimeters, then I drew a line for the wingspan here, because that's what A is asking, the wingspan, find the actual length of the wingspan to the nearest foot. So I'm using the 10 feet scale. Okay, so that's 9.2 centimeters. Well, I need to find out how many 10 feet increments that is. So I know that every 2 centimeters is equal to 10 feet. So I find how many 2 centimeters goes into 9.2, which is 4.6. So now I know for each of those, you multiply that by 10 feet to get the actual length. So 4.6 times 10 equals 46 feet. So that's the actual wingspan. Okay, the height of the plane. So once again, using the same scale, it wants it in foot or to the nearest foot. So the height I measured was 2.4. So I'm going to do the same procedure. I need to find out how many 2 centimeters are in 2.4. And that comes out to be 1.2. So now I'm going to multiply that 1.2 by 10 to get my actual feet. So 1.2 times 10 is 12 feet. Okay, and last, it's asking for the full length of the plane. So once again, it does want it in the nearest meters, so I have to use the meters scale. So it does say, so when I measured that 7 meters, it came out to be about 4.2 centimeters. So then I measured the full length, it was 5.7 centimeters. So likewise, I have to see how many times 4.2 centimeters goes into 5.7 centimeters, and when you do that, you get roughly 1.36. So now that I know that, I have 7 meters 1.36 times. So you're going to multiply those together and come out with about 9.5 meters. Okay, once again, your sheet of paper, you might have got a little bit different reading, so there might be a little bit different, a little bit of a difference, but your answer should be fairly close to those numbers. Okay, the next one, it says a blueprint for the building includes a rectangular room that measures 3 inches long and 5.5 inches wide. The scale for the blueprint says that 1 inch on the blueprint is equivalent to 10 feet in the actual building. What are the dimensions of this rectangular room in the actual building? Okay, so all we have to do here is multiply our drawing dimensions by our scale factor, which is 10 feet. So for every inch is 10 feet. So if we have 3 inches, there's 10 feet for each of those. So 3 times 10 is 30 feet. Likewise with the 5.5, we do the same thing. We're going to multiply it by 10, and we get 55 feet. All right, number 3, it says here is the scale map of Lafayette Square, a rectangular garden north of the White House. Okay, we need to find the dimensions of the sides. So it gives us the scale down here. So I use the centimeter side, and on my scale, it showed that that was about 3 centimeters. And now on the drawing, I took it that kind of the line that I drew was the edge. There is this dotted white line. If you measured from there to there, your answers might be a little bit different, but they shouldn't. Maybe add 100 or 2, add at the most maybe 200 to this, but it should be somewhere in that ballpark. Sorry, that side was the 400, so it should be close to 400. The length should be somewhere close to 680. Once again, depending on where you measured, it might be a little different. Okay, so I measured this top length, and that was 10.2. And down here, I know that 3 centimeters is equal to 200 feet. So I need to find out how many 3 centimeters goes into 10.2, and that's 3.4. And so now I have 3.4 lengths of that, which each equals 200. So I take 3.4 times 200, and you get 680 feet. I'm going to follow the same steps here with the width of Lafayette Square. So I measured it was 6 centimeters. 3 centimeters can go into that twice. So I have this length down here on the scale of 200 feet twice. So that would be 2 times 200, which gives me 400 square feet. Or sorry, not square feet, but 400 feet. All right, and then B, it says use an inch ruler to measure the line segment of the graphic scale. About how many feet does 1 inch represent on the map? So this is where I measured 1 inch came to right this first tick mark right here. And so it's in between 100 and 200 feet, closer to 200. So it's about 170 feet. That one you might have varied a little bit. You might have said 180, 160, but it should be somewhat close. All right, and then the last problem, it says, here's a triangle A. Lynn created a scale copy of the triangle A with an area of 72 square units. How many times larger is the area of the scale copy compared to that? Oh, excuse me. Of triangle A. Well, we need to find the area of this first, so we know that the base is 3 units, the height is 3 units. Area of a triangle is base times height divided by 2, or base times height times 1/2. My base is 3, my height is 3. That equals 9. 9 times 1/2, or half of 9, is 4.5. Okay, so this is going to be similar to the one we did in lesson 6, practice problems. So we went from 4.5 to 72. Okay, this one we're getting bigger, so now we are increasing, so it has to be greater than 1. So 72 divided by 4.5, once again, is 16. So that is how much larger, or how many times larger, that 72, or the scale drawing of this triangle is, than the original. Now that 16 is not the scale factor, so that's in B, that's what we're finding. The scale factor, or the area, is always multiplied by the scale factor squared. So the square root of 16 is 4, so then the scale factor would actually be 4. So think back to those blocks that we used when you doubled the size of each length. You actually it was actually 4 times the area of the original. Okay, same thing applies here. Okay, so now that the square root of 16 gives us 4, so that now our scale factor was actually 4. Okay, then so now that we have that, we can answer C. It says, what is the length of the bottom side of the scaled copy? Well, we know the original is 3, and we have to multiply the original lengths by our scale factor. So 3 times 4 gives us 12. All right, and that is the answer key to that worksheet.